Hello there, and welcome to the Sleepy Science Facts. Tonight, we will gently drift into the farthest reaches of outer space, exploring some of the most distant galaxies ever discovered. These immense collections of stars, shaped by gravity and ancient cosmic forces, stretch back toward the earliest moments of the universe. When we look in their direction, we are looking across distances so vast they are almost impossible to imagine, and into a deep past when the universe was still beginning to understand what it would become. Distant galaxies carry quiet stories of creation and transformation. They show how matter slowly gathered across space, how the first stars ignited, and how structure gradually emerged within the young cosmos. Some glow with youthful energy, bright and active. Others appear calm and settled, having long since passed their most luminous days. Each one offers a small but meaningful clue about how the universe evolved, and how our own cosmic home fits within that much larger picture. If you enjoy these gentle journeys, you might consider leaving a like, subscribing, or sharing a quiet thought below. It helps others find their way here as well, one sleepy soul at a time. But for now, there is nothing you need to do. Simply settle in. Let your shoulders soften, let your breathing slow, and allow your thoughts to loosen their grip. As your eyes begin to grow heavy, join me as we wander through the cosmos together. Let's begin. The farthest galaxies we observe are also the earliest chapters of the universe. When a telescope captures their light, it is receiving a message that began its journey when the cosmos was still very young. This means that distance and time are deeply intertwined. Nearby galaxies show us the universe in its later, calmer years, while more distant ones reveal it during its restless childhood, when everything was smaller, hotter, and still taking shape. Astronomers build a kind of timeline by comparing these different distances, watching for patterns that change with age. In doing so, they can observe stars being born, shapes settling from chaotic to orderly, and the first heavy elements spreading outward from dying stars. It is, in a sense, history written in photons, and the remarkable part is that these pages have not disappeared. They continue arriving night after night, right on schedule. Some distant galaxies shine from a time before our sun even existed. Our sun is only about 4.5 billion years old. Yet many galaxies we observe are so far away that their light began traveling long before the sun and earth were formed. In that era, the Milky Way was still assembling itself, and the periodic table was missing many of the elements we now take for granted. Early generations of stars had to do that work first, forging heavier elements in their cores and then scattering them into space through powerful explosions. Those enriched atoms would later become planets, oceans, and even living cells. When you look at a galaxy from that distant time, you are seeing a universe that has not yet learned how to create a world like ours. That is why distant galaxies feel so profound. They show us what had to happen before we could ever exist. A single deep image of the sky can contain thousands of galaxies at once. A patch of darkness that appears empty to the naked eye can be filled with countless distant systems when a telescope observes it long enough. Deep images work like patient listening. They collect faint photons one by one, stacking hours of exposure until whispers of light become visible. In famous deep-field observations, the area of sky captured is often smaller than the width of your little finger held at arm's length. Yet within that tiny slice, you can find spirals, ellipticals, and irregular galaxies, all at different distances and stages of life. Some are close enough to reveal detail. Others are barely more than a faint glow. Together, they reveal a quiet but powerful truth. The universe is not lightly sprinkled with galaxies. It is filled with them. And once you understand that, the night sky never feels empty again. Many distant galaxies appear distorted because gravity bends their light. On the largest scales, gravity can act like a natural lens. A massive galaxy or cluster can curve space so strongly that light from a more distant galaxy is forced to travel along bent paths. To us, that background galaxy may appear stretched into an arc, duplicated into multiple images, or even shaped into a near-perfect ring. These are not visual illusions. They are precise maps of invisible mass. By measuring the shape of this distortion, astronomers can estimate the mass of the lensing object and trace where its matter lies, even when most of that matter emits no light at all. Lensing can also magnify distant galaxies, making otherwise unreachable objects bright enough to study in detail. In this way, gravity becomes both a sculptor and a guide, helping us see farther than our instruments alone would allow. The most ancient galaxies often appear red because space itself stretches their light. As the universe expands, it stretches the waves of traveling light, shifting them toward longer, redder wavelengths. A galaxy that once shone brightly in ultraviolet light may arrive at our telescopes appearing red, or even invisible to instruments tuned for visible light. That is why infrared observatories are so important. They are designed to detect this stretched starlight that would otherwise pass unnoticed. Red color can also hint at age. Older stars tend to be cooler and redder than hot, newly formed ones. Astronomers carefully separate these effects by observing galaxies through multiple filters and comparing the results to models of how stars evolve. In doing so, they can turn a simple color shift into an estimate of distance and into a clue about when a galaxy's stars first began to shine. A faint reddish glow can be the signature of something incredibly ancient. Collisions between galaxies were far more common in the early universe than they are today. In those early times, galaxies were closer together, and their paths crossed more frequently. Gravity drew them into slow, graceful encounters that unfolded over millions of years. At first, there was gentle stretching, long streams of stars and gas pulled outward by tidal forces. Then came the mixing, as orbits shifted and clouds collided. These events did not always destroy galaxies. More often, they transformed them. A thin disk could become thicker. Two smaller systems could merge into one larger one. Fresh gas could be driven inward, igniting intense bursts of star formation in regions that were once quiet. When astronomers look far into the past, they find a wide variety of distorted shapes that reflect a universe still under construction. Collisions were not accidents. They were part of the plan. And even today, galaxies still carry the subtle marks of those ancient encounters, hidden beneath their calm and orderly appearances. A galaxy's color can quietly reveal whether it is still creating new stars or slowly settling into rest. Color in space is not merely decoration. It is a clue about which kinds of stars are shaping the light we see. When a galaxy is actively forming stars, it often appears bluer because young, hot stars release intense, energetic light. As star formation slows, those bright blue stars fade quickly, and longer-lived, redder stars begin to dominate the glow. Astronomers measure these subtle differences using carefully chosen filters, then compare the results to models of stellar populations. In a sense, it becomes a kind of mood reading, but one grounded entirely in physics. Some galaxies seem to be in the middle of a busy construction phase. Others feel quiet, like a town after a celebration has ended. Even dust leaves its own signature, altering light in a different way than aging does. With just a few bands of color, a galaxy can reveal whether it is active, resting, or quietly hiding its activity behind a veil. In the early universe, galaxies grew quickly through constant mergers and a steady supply of fresh gas. Back then, growth was less like a peaceful suburb and more like rush-hour traffic. Small galaxies were everywhere, and gravity kept drawing them together. When two galaxies met, their stars rarely collided, because the distances between stars are so vast. Instead, their gas clouds interacted, compressing, colliding, and mixing. At the same time, new gas flowed in from the surrounding cosmic environment, fueling even more star formation and adding mass. This continuous inflow allowed early galaxies to grow rapidly, even when individual components were relatively small. Over time, repeated encounters could transform loose clumps into larger, more organized systems. Astronomers search for evidence of this rapid growth by studying the shapes of distant galaxies and the way their gas and stars are distributed. It is a story of construction under pressure, where material kept arriving and the design kept evolving. Some distant galaxies are hidden in plain sight, concealed behind cosmic dust. Dust is made of tiny particles, closer to smoke than to sand, and it is remarkably effective at blocking visible light. In distant galaxies, it can wrap around star-forming regions and obscure them almost completely. To a visible light telescope, such a galaxy may appear faint and unremarkable. But when observed at longer wavelengths, the picture changes entirely. Dust absorbs energetic starlight, warms up, and then releases that energy again as infrared radiation. Instruments sensitive to those wavelengths can reveal galaxies that are forming stars at astonishing rates, even though they look dim in ordinary images. This is one reason our understanding of the universe has evolved with new technology. Dust does not simply decorate galaxies. It hides some of the most active ones. By looking through it, we uncover a more complete view of how rapidly galaxies can grow behind that curtain. There was once a period in cosmic history when star formation reached a peak, almost like a universal season of fireworks. During this era, galaxies were especially active. They were rich in cold gas, which could collapse into new stars much more easily than it does today. Frequent interactions and mergers helped compress this gas even further, triggering bursts of star formation. Over time, that intensity faded. Gas supplies were depleted, heated, or pushed away, and the average rate of star formation declined. The universe did not stop forming stars. It simply became slower, more measured, and more selective. Understanding when this peak occurred helps explain why galaxies look the way they do today. The same telescope can reveal both young galaxies and mature ones in a single view. A nearby galaxy might display clear spiral arms and stable regions of star formation, while a much more distant one in the same image may appear smaller and more chaotic, because we are seeing it at an earlier stage of cosmic time. The instrument itself has not changed. The light has. Different distances correspond to different ages, and the telescope simply records whatever arrives. This allows astronomers to compare young and old systems without changing methods or instruments. It is like looking at a family portrait that includes infants, adults, and elders all at once. That mixture makes patterns easier to recognize and differences easier to trust. Some distant galaxies appear as faint smudges, yet contain billions of stars. In deep images, certain galaxies barely stand out from the background, like a soft fingerprint on darkness. But their faintness is not a sign of small size. It is a consequence of distance. Light spreads out as it travels, and its brightness becomes diluted across an enormous volume of space. Add dust, aging stars, and the limits of our detectors, and even a massive galaxy can appear subtle and quiet. Astronomers extract meaning from that faint glow by measuring its shape, color, and how its brightness changes across the image. From those clues, they estimate how many stars must be present. It is a striking realization. A tiny blur can represent a vast city of suns. The universe often hides its greatest structures inside its quietest signals. Some galaxies appear extraordinarily bright because something powerful is feeding at their core. At the center of many galaxies lies a supermassive black hole. When gas begins to fall toward it, the process is anything but quiet. Instead of disappearing immediately, the material forms a dense, swirling disk where friction heats it to extreme temperatures. This disk can shine with such intensity that it outshines all the stars in the galaxy combined, turning the center into a beacon visible across billions of light years. This is how quasars reveal themselves. Their energy does not come from nuclear fusion like stars, but from gravity itself, converting infalling matter into radiation with remarkable efficiency. In some cases, their brightness changes over weeks or months, suggesting that the emitting region is relatively small. That flickering becomes a clue, hinting at the true scale of the engine. When you observe one of these luminous cores, you are witnessing a galaxy with an active heart, feeding and radiating across the darkness. Some galaxies eventually become quenched, meaning that the formation of new stars has largely stopped. A quenched galaxy is not lifeless. Its existing stars continue to shine for billions of years. What has changed is the supply of new stars. In some cases, the galaxy has used up much of its cold gas. In others, that gas has been heated so strongly that it can no longer collapse into new stellar nurseries. Sometimes energetic processes in the galactic center or conditions in the surrounding environment prevent fresh gas from settling in. The result is a system dominated by older stars, with fewer bright young ones to refresh its glow. Astronomers identify these galaxies through their colors, their spectra, and the absence of clear signs of newly formed stars. This stage marks an important turning point. It is the moment when a galaxy stops building and begins aging with what it already has. Interestingly, spiral structures can appear earlier than we might expect. Spiral galaxies often feel like a finished product, something that requires time and stability to develop. That is why it can be surprising to find clear spiral patterns in distant galaxies, from an era when the universe was younger and more chaotic. Spirals are not fixed shapes painted onto a galaxy. They are patterns that emerge from motion, as stars and gas orbit within a rotating disk and gravitational waves ripple through it. For such a disk to form, a galaxy must settle its gas into a relatively flat, organized structure rather than remaining a turbulent cloud. Seeing spiral forms early suggests that some galaxies reached that balance more quickly than expected. It also raises questions about what allowed them to remain stable in an environment filled with frequent interactions. Many early galaxies appear clumpy because their gas collapses into large, bright regions. Instead of smooth spiral arms, distant galaxies often look like scattered islands of light. These bright patches are usually enormous star-forming regions, much larger than similar structures in nearby galaxies. In the early universe, galaxies contained large amounts of gas, and that gas could become unstable, breaking into massive clumps under its own gravity. Within each clump, stars formed rapidly, causing the region to shine intensely. Over time, these clumps could move, merge, and migrate toward the center, helping to reshape the galaxy's structure. Astronomers study this clumpiness as a clue to how galaxies built their inner regions and transformed chaotic material into organized systems. These clumps are not random noise. They are visible signs of a young galaxy doing the heavy work of formation. Some galaxies appear small, but contain enormous amounts of mass packed into a tight space. At first glance, they may seem compact and unremarkable, but closer analysis reveals intense gravity and rapid internal motion. This means stars are densely packed, and the dynamics inside the galaxy can be extreme. Astronomers detect this by measuring how light is concentrated and by studying spectral lines that reveal how fast stars and gas are moving. These compact galaxies are especially intriguing because they may represent early stages of today's massive systems, caught during a brief and intense phase. They raise important questions about how such density forms without tearing the system apart. Giant elliptical galaxies often form through repeated mergers rather than calm growth. Although they appear smooth and quiet, their histories can be turbulent. Multiple mergers can scramble stellar orbits, replacing orderly rotation with motion in many directions. Over time, this creates a rounded, featureless glow. In some cases, faint traces remain, subtle ripples or shells that hint at past interactions. These features act like wrinkles that never fully disappear, preserving a memory of earlier events. Dwarf galaxies may be small, but they play a crucial role in cosmic history. Because they contain fewer stars and have weaker gravity, they respond more dramatically to changes in their environment. Their gas can be lost more easily, their star formation can be irregular, and their chemical composition can remain simpler for longer periods. This makes them valuable time capsules. Some dwarf galaxies preserve evidence of early star formation and chemical evolution more clearly than larger systems that have undergone many mergers. They are also thought to be building blocks, smaller units that larger galaxies grow from over time. By studying them, astronomers gain insight into how galaxies assemble and evolve. Dwarf galaxies can sometimes be torn apart by the gravity of larger neighbors, leaving behind long streams of stars. Gravity is not always gentle. When a smaller galaxy orbits a larger one, tidal forces can stretch it, and over time, repeated passes can pull stars away. Those stars do not disappear. Instead, they form long, thin streams that wrap around the host galaxy, sometimes extending across vast regions of space. These stellar streams are more than beautiful structures. They are evidence that galaxies continue to grow by absorbing smaller companions. They also act as tracers of invisible mass. Their paths are shaped by the gravitational field of the host galaxy, including its dark matter halo. By mapping these streams, astronomers can better understand how mass is distributed, even when it cannot be seen directly. Even after a dwarf galaxy is mostly dissolved, its stars can still trace its former orbit, preserving a memory of what once existed. The Milky Way is just one island among countless others in a vast cosmic ocean. It is natural to think of our galaxy as central, simply because we live inside it. But observations have shown that galaxies fill space in every direction. Even a region of sky that appears empty can contain countless distant systems. Each galaxy is its own environment, with its own history of star formation, chemical change, and gravitational interaction. Some are small and faint. Others are enormous and densely packed with stars. When we call the Milky Way an island, we also acknowledge that it is only one among many. The night sky becomes less like a blank canvas and more like a map of distant places. Galaxy groups are common, and true isolation is rare. Many galaxies do not exist alone, but are bound together in small groups by gravity. Within these groups, galaxies can pass close enough to influence one another, pulling on gas and stars, and sometimes creating faint streams. Even without collisions, these interactions can alter orbits and affect how gas flows into each system. Some galaxies become dominant members of the group, while others become satellites or gradually lose material over time. This matters because our own galaxy is part of such a group as well. By studying distant galaxy groups, astronomers can compare different environments and understand what conditions lead to growth, decline, or transformation. Galaxy clusters represent an even larger scale of structure. A cluster can contain thousands of galaxies, along with enormous amounts of hot gas and unseen mass. The space between galaxies in a cluster is filled with extremely hot gas that emits X-rays due to its high temperature. Inside this environment, galaxies move at high speeds, and frequent interactions can alter their shapes, strip away gas, and reduce star formation. Clusters are not just collections. They are dynamic systems that reveal how matter gathers on the largest scales. Between these dense regions lie vast cosmic voids where galaxies are scarce. If clusters are like crowded cities, voids are like quiet countryside stretching across millions of light years. They are not completely empty, but matter within them is spread very thinly. These regions formed from small differences in density in the early universe. Denser areas pulled in more material and became clusters, while less dense areas lost that competition and became emptier over time. Studying voids helps astronomers understand how structure developed and how matter is distributed across space. Even emptiness has a pattern, and even the quietest regions carry information. On the largest scales, galaxies trace a vast cosmic web. They are not randomly scattered, but arranged along filaments and sheets that connect clusters together. These structures form an enormous network across the observable universe. You can imagine galaxies as glowing points along invisible threads. Those threads exist because matter flowed along preferred paths shaped by gravity and the initial conditions of the early universe. Gas followed these same paths, and where gas collects, stars can form. This means the cosmic web is not just a map of where galaxies are, it is also a map of where they can grow. Astronomers reveal this structure by surveying large regions of space and mapping the positions of millions of galaxies in 3 dimensions. The result is both visually striking and scientifically powerful. It explains why clusters sit at intersections of filaments, why voids form between them, and why the universe resembles a network rather than a uniform distribution. Our own galaxy is part of this web, carried along one of its vast strands. Dark matter halos act as an invisible framework that guides where galaxies form. The stars we see in a galaxy are only part of the story. Most galaxies appear to sit within much larger halos of unseen mass. This dark matter does not emit or absorb light, yet it exerts gravity. That gravity pulls ordinary gas into growing structures and helps hold it in place long enough for stars to form. Without this hidden scaffolding, many galaxies would struggle to assemble as efficiently as they did. Dark matter halos also influence the shape of galaxies and the motion of their stars. In simulations, galaxies tend to form where dark matter first gathers, with visible matter following the gravitational blueprint. Although astronomers cannot directly image these halos, they can detect their presence through motion and gravitational lensing. The idea is simple, but its implications are profound. Much of the universe's structure is built from something we cannot see. We understand it by observing how everything else behaves. One of the strongest clues comes from how galaxies rotate. If we measured only the visible stars and gas, many galaxies should not hold together. Their outer regions move too quickly for the gravity of visible matter alone to keep them bound. Instead of slowing down with distance from the center, the rotation speed often remains steady. This unexpected result points to a large, extended reservoir of mass surrounding the galaxy. This conclusion does not depend on a single observation. It appears consistently across many galaxies and different measurement techniques. Dark matter becomes the simplest explanation that fits all of the data. The result is a striking shift in perspective. The visible part of a galaxy is only a small fraction of its total mass. Gravitational lensing offers another way to detect this hidden matter. When a massive object lies between us and a distant galaxy, its gravity can bend the background light into arcs or rings. The exact shape of these distortions depends on how mass is distributed in the foreground object. By modeling these shapes, astronomers can reconstruct the mass distribution, including both visible matter and dark matter. In many cases, the visible matter accounts for only a small portion of the total. Lensing is powerful because it does not depend on light emission. Gravity bends light regardless of whether the mass is visible or not. In this way, distant galaxies act like backlights, revealing the invisible structure in front of them. Sometimes lensing also magnifies distant galaxies, making them easier to study. A galaxy that would otherwise be too faint can become bright enough for detailed observation. This allows astronomers to analyze its structure, composition, and motion in ways that would not be possible otherwise. It is as if the universe itself provides a natural telescope, extending our reach beyond the limits of our instruments. In some cases, lensing can even create multiple images of the same galaxy. Light can take different paths around a massive object, arriving at different times. If the background galaxy changes in brightness, those changes can appear in each image at different moments. This creates a natural timing experiment, allowing astronomers to test models of gravity and cosmic expansion. It is one of the most fascinating consequences of curved space. Quasars are among the brightest objects in the universe because of the extreme processes near black holes. Their intense light can travel across vast distances, passing through clouds of gas between galaxies. As it does, that gas leaves subtle absorption features in the quasar's spectrum. These features act like fingerprints, revealing the composition and distribution of matter along the line of sight. In this way, quasars become tools for studying the otherwise invisible regions of space between galaxies. Instead of trying to observe faint gas directly, astronomers let bright distant sources illuminate it. The result is a layered record of the universe, built from the light that has traveled across it. Some active galactic cores flicker over time as material continues to fall into their central black holes. An active galactic nucleus can change brightness on timescales that are surprisingly short, even within a human lifetime. This variability is incredibly useful. Rapid changes suggest that the emitting region must be compact, because a large region cannot brighten or dim all at once. Astronomers observe these fluctuations across different wavelengths, measuring how changes in one band echo in another. These delays are not random. They act like a ruler, revealing the distances between regions near the black hole, including the hot inner disk and the surrounding clouds of gas that respond to its radiation. This technique is known as reverberation mapping, and it allows scientists to estimate the mass of the black hole without directly imaging it. Rather than a steady flow, the feeding process is uneven, dynamic, and sometimes chaotic. When the core flickers, it is a sign that the central engine is active, constantly adjusting as matter falls inward. In some galaxies, powerful jets emerge from the regions near black holes and extend far beyond the galaxy itself. These jets are narrow streams of particles moving at nearly the speed of light. They can travel enormous distances, pushing out of the host galaxy and into intergalactic space, sometimes stretching far beyond the galaxy's own size. As they move, they emit radiation produced by charged particles spiraling along magnetic fields. At their endpoints, they can inflate vast lobes of energy and create bright hotspots where they collide with surrounding gas. Even if the stars in a galaxy appear calm, these jets reveal intense activity at its center. They are one of the clearest signs that a black hole is actively interacting with its environment. In some cases, these jets can influence the entire galaxy by heating gas and preventing it from forming new stars. When gas is kept too hot or too turbulent, it cannot collapse into dense clouds. This creates a feedback effect, where energy from the central black hole regulates star formation across the galaxy. In galaxy clusters, this process can be observed as cavities in hot gas, showing where jets have pushed material aside. It is a subtle but powerful mechanism, helping explain why some large galaxies stop forming new stars, even when gas is still present. Some galaxies hide their central activity behind thick layers of dust and gas. From the outside, these galaxies can appear quiet and unremarkable, but at their core, intense processes may still be taking place, obscured from direct view. Astronomers reveal these hidden regions by observing wavelengths that can penetrate dust, such as infrared and X-rays. Infrared observations detect warm dust that has absorbed energy and re-emitted it, while X-rays can pass through dense material that would block visible light. This reveals a more complete picture of galactic activity. It shows that some of the most energetic processes in the universe occur out of sight, hidden behind cosmic curtains. Infrared telescopes, in particular, reveal dust heated by stars, glowing like embers in the dark. When young stars form inside dusty regions, much of their light is absorbed. The dust warms and re-emits that energy at longer wavelengths, allowing astronomers to detect star formation that would otherwise remain invisible. By measuring this infrared glow, scientists can estimate how much star formation is taking place, even when direct light is obscured. This is especially important for distant galaxies, where dust often hides the most active regions. In this way, infrared observations provide a more honest account of how busy the universe has been in forming stars. Radio telescopes offer yet another perspective by tracing cold gas, the raw material for star formation. Neutral hydrogen emits a characteristic signal in radio wavelengths, while molecular gas can be detected through emissions from molecules like carbon monoxide. These signals reveal not just how much gas is present, but how it moves within galaxies. They can show rotation, inflows, and disturbances caused by interactions. Sometimes a galaxy that appears quiet in visible light contains a large reservoir of cold gas, ready to fuel future star formation. Radio observations turn that invisible supply into something we can map and understand. In this sense, star formation becomes less mysterious. It depends on available fuel and the conditions that allow that fuel to collapse into stars. Ultraviolet light highlights young, hot stars, but it is easily blocked by dust. Massive stars emit strongly in ultraviolet wavelengths, making this light a direct indicator of recent star formation. However, dust absorbs ultraviolet radiation very efficiently, which can hide ongoing activity. To overcome this, astronomers combine ultraviolet and infrared data. The ultraviolet shows what escapes, while the infrared reveals what was absorbed and re-emitted. Together, they provide a more complete picture of star formation. By combining observations across multiple wavelengths, astronomers can reconstruct the full story of a galaxy. No single type of light can reveal everything. Visible light shows stars, infrared reveals dust and hidden activity, radio traces gas, and X-rays highlight extreme environments. When these perspectives are combined, they create a layered understanding of how galaxies evolve. A galaxy may appear calm in one wavelength and turbulent in another. Only by bringing all of these views together can we understand what is truly happening. Redshift acts as a kind of cosmic speedometer, revealing how fast galaxies are moving away from us. Light carries subtle information about motion. When a galaxy recedes as space expands, its light is stretched toward longer, redder wavelengths. Astronomers measure this shift by spreading light into a spectrum and identifying familiar patterns from elements such as hydrogen. Those patterns appear slightly displaced, and the amount of that displacement tells us how strongly expansion has stretched the light during its journey. It is similar in spirit to how the pitch of a siren changes as it moves away, except here, the effect is encoded in color rather than sound. With redshift, a distant galaxy becomes more than a faint glow. It becomes a data point in the larger pattern of cosmic expansion. When many galaxies are measured together, they reveal how the universe itself is growing over time. Greater redshift generally means greater distance and an earlier moment in cosmic history. Because light takes time to travel, observing distant galaxies is also observing the past. Redshift allows astronomers to arrange these observations into a sequence, placing galaxies along a timeline. Systems with higher redshift are usually seen as they were earlier, while lower redshift galaxies show later stages of development. This makes it possible to compare how galaxies change over time, from irregular, youthful structures to more stable and familiar forms. There are small complications due to local motions, but the overall pattern remains clear and powerful. The sky becomes a layered archive, where looking farther also means looking deeper into time. The expansion of space can cause galaxies to recede faster than light without violating physics. This idea may seem to contradict fundamental limits, but it involves a different kind of motion. Relativity restricts how fast objects can move through space, but it does not limit how quickly space itself can expand. As a result, the distance between distant galaxies can increase at an effective rate greater than the speed of light. No galaxy is outrunning light locally. Instead, the space between them is stretching. This explains why there are regions of the universe that are permanently out of reach, even in principle. It also explains why some galaxies are visible only because their light began traveling when the universe was smaller. We never observe galaxies as they exist now, only as they were when their light was emitted. Every observation is a message from the past. For nearby galaxies, that delay is still immense on a human scale. For distant ones, it reaches billions of years. This means a single image of the sky can contain objects from very different eras. This is not a trick of interpretation, but a direct consequence of the finite speed of light. Astronomers use this property to reconstruct cosmic history, comparing galaxies across distances and times. Sometimes the galaxy we observe has already changed dramatically, or even ceased to exist in its original form. Light does not update itself as it travels. It carries only the information from the moment it was emitted. Over billions of years, a galaxy could merge, transform, or be disrupted, while its earlier light continues its journey. This creates a kind of cosmic delay, where we observe ancient states long after they have passed. Astronomers take this into account when studying evolution, treating each distant galaxy as a snapshot from a specific moment in time. It is like receiving postcards sent across vast stretches of history, each one capturing a moment long gone. Starlight can travel for billions of years, yet it is detected in an instant. A single photon may spend most of the universe's history in transit, moving across expanding space and between galaxies. Then, in a brief moment, it reaches a telescope and is recorded. This contrast between immense travel time and instant detection is part of what makes astronomy so remarkable. A deep observation is essentially an accumulation of countless such arrivals. Each photon contributes a small piece of information, and together they form an image, a spectrum, and a story. Every detected photon is also evidence that the universe remains transparent enough for light to cross vast distances. When you observe a distant galaxy, you are participating in an exchange that began long before humans existed. A galaxy's spectrum can reveal its composition, like a barcode of elements. When starlight is separated into its component wavelengths, it shows patterns of absorption and emission. These patterns correspond to specific elements, such as hydrogen, oxygen, and carbon. By analyzing them, astronomers can determine what a galaxy is made of, even from great distances. Spectra also carry information about temperature, density, and motion, because the lines shift and broaden under different conditions. This makes spectroscopy one of the most powerful tools in astronomy. It transforms faint light into detailed physical knowledge, turning distant galaxies into measurable systems rather than simple points of light. Early galaxies contained fewer heavy elements because stars had not yet had enough time to produce them. In the beginning, most of the universe consisted of hydrogen and helium, with only tiny traces of heavier elements. The materials needed for rocky planets and complex chemistry are created inside stars and released into space over time. A star must first live its life, fuse lighter elements into heavier ones, and then return that material through stellar winds or explosive events. Because this process takes time, early galaxies had not yet been enriched by many generations of stars. Astronomers can detect this difference by studying spectra, where certain elemental signatures appear weaker in more primitive systems. This also affects how gas behaves. With fewer heavy elements, cooling becomes less efficient, which can influence how stars form. For this reason, early galaxies are not simply younger versions of modern ones. They operated under different conditions, with a more limited chemical toolkit. That difference shaped how quickly they could build structure, form dust, and create the ingredients for future star systems. The first generations of stars transformed galaxies by enriching their gas. These early stars formed in a simpler universe and played a crucial role in changing it. As they aged, they produced heavier elements in their cores and released them into their surroundings. This enrichment allowed gas to cool more effectively, making it easier for new stars to form. It also enabled the formation of dust and more complex chemical compounds. Astronomers traced this transition by observing galaxies at different stages and measuring how their chemical composition evolves. With each new generation of stars, galaxies became more diverse and more capable of forming complex structures. In this sense, the first stars were not just sources of light, they were builders, reshaping their galaxies from within. Supernova explosions can regulate how quickly a galaxy grows. When massive stars reach the end of their lives, they explode with tremendous energy. In smaller galaxies, this energy can heat or even expel gas, reducing the material available for new star formation. If gas is pushed out entirely, star formation slows significantly. If it is only heated, it may take time before it cools enough to form new stars again. This creates a cycle of activity and pause, especially in dwarf galaxies. Supernova feedback acts as a kind of control mechanism, preventing galaxies from forming stars too rapidly all at once. It also affects chemical evolution, because enriched material can be lost before it fully mixes into the galaxy. Some galaxies experience intense bursts of star formation known as starbursts. During these periods, star formation accelerates dramatically. Gas is compressed into dense regions where it rapidly forms new stars. These regions can become crowded with massive, short-lived stars that strongly influence their surroundings. In distant galaxies, starbursts can make systems glow brightly in infrared light, as dust absorbs energy and re-emits it as heat. However, these phases are brief. They consume gas quickly and generate feedback that eventually slows the process. This makes them valuable for understanding extreme conditions in galaxy evolution. Starbursts are often triggered by interactions and mergers between galaxies. When galaxies pass close to one another, gravity can disrupt their gas, driving it inward and increasing density. As gas streams collide and compress, conditions become ideal for rapid star formation. This process can produce bright clusters of young stars in regions where gas has been concentrated. At the same time, the interaction disturbs orbital motion, increasing the likelihood of further collisions between gas clouds. These events can send waves of star formation through the system. Eventually, the same processes that triggered the burst can help bring it to an end, as energy from stars and supernovae disperses the remaining gas. In this way, a merger acts both as a spark and a limit, shaping the life cycle of a galaxy. Some distant galaxies are surrounded by vast glowing clouds of gas. These extended nebulae can stretch far beyond the visible stars, forming a kind of luminous halo. Their light often comes from gas excited by young stars or energetic activity near the galaxy's center. By studying these regions, astronomers can map how gas moves, whether it is flowing inward to fuel future star formation or outward as part of galactic winds. These structures make galaxies feel less like isolated objects and more like systems connected to their surroundings. The stars form the bright core, but the surrounding gas is where growth and change continue to unfold. Some galaxies allow ultraviolet light to escape, helping transform the early universe. In the earliest epochs, space between galaxies was filled with neutral hydrogen, which absorbed energetic light very efficiently. For the universe to become transparent, enough high-energy photons had to escape from galaxies and ionize this gas. Not all galaxies could do this. Ultraviolet light is easily blocked by dust and dense clouds within galaxies themselves. Escape becomes more likely when powerful stellar winds or supernova explosions carve openings through the gas. It can also happen when star formation occurs near the outer edges of a galaxy, where there is less material to block the radiation. Astronomers search for these leaky galaxies by analyzing spectral signatures that suggest ultraviolet photons are escaping. These galaxies are not just interesting anomalies. They may have played a key role in a major cosmic transition. This transition, known as reionization, ended the cosmic dark ages and made the universe more transparent to light. After the universe cooled enough for protons and electrons to combine, much of the gas became neutral. This neutral gas absorbed ultraviolet radiation, limiting how far light could travel. Over time, early stars and galaxies produced enough energetic radiation to ionize hydrogen once again. This process spread outward in growing regions until most of the intergalactic medium became ionized. Once this happened, light could travel more freely, allowing us to see deeper into space. Reionization was not just a moment in time. It influenced how galaxies formed and evolved afterward. Astronomers reconstruct this era using evidence from distant galaxies, quasars, and the cosmic microwave background. It represents one of the universe's major transformations, similar to a cosmic dawn spreading across space. Hydrogen absorption lines allow astronomers to map invisible gas between galaxies. Even when intergalactic gas is too faint to detect directly, it can still leave its mark on light passing through it. When light from a distant source travels through hydrogen clouds, certain wavelengths are absorbed. This creates a pattern of absorption features in the spectrum. By measuring these features, astronomers can determine the distribution and motion of gas along the line of sight. Each absorption line corresponds to gas at a different distance, creating a layered record of the universe. This method transforms a single beam of light into a probe of cosmic structure. Instead of only observing what shines, astronomers can also study what blocks light. In this way, the universe becomes readable through both emission and absorption. Intergalactic gas traces the same large-scale structures as galaxies. Both are shaped by gravity, forming filaments, clusters, and vast empty regions. By combining many lines of sight, astronomers can reconstruct a three-dimensional picture of this gas. This technique, similar to tomography, reveals how matter is distributed across space. The gas is not just background scenery. It is the reservoir that feeds future star formation. It also carries heavy elements outward from galaxies through winds and outflows. By studying this faint medium, astronomers can ask deeper questions. Where does a galaxy's next supply of gas come from? Where does its expelled material go? The answers are written in the thin, structured mist between galaxies. Metallicity, the abundance of heavy elements, tends to increase over time. Each generation of stars processes gas, creating heavier elements and returning them to the galaxy. Over time, this enriches the material that forms new stars. Astronomers measure metallicity by analyzing emission lines from gas in star-forming regions. Across cosmic history, a clear trend emerges. Earlier galaxies tend to have lower metallicity, while later ones are more enriched. However, this increase is not uniform. It depends on how efficiently a galaxy forms stars, how much gas flows in, and how much is lost through outflows. Metallicity becomes a record of a galaxy's past behavior. Smaller galaxies often lose heavy elements more easily. Because their gravity is weaker, energetic events can push enriched gas out into space. This means they may remain chemically simple even after forming stars. Astronomers study this effect by comparing metallicity to galaxy mass and searching for evidence of outflows. The result is a vivid picture. Some galaxies enrich themselves steadily, while others lose much of what they produce. In contrast, massive galaxies can retain enriched material more effectively. Their stronger gravity holds gas in place, allowing it to cool and fall back inward. This recycling process, sometimes described as a galactic fountain, helps build up heavy elements over time. These galaxies can also maintain extended halos of hot gas that trap outflows and mix them gradually. This leads to a more consistent and steady chemical evolution. The difference between small and large galaxies is not simply about size. It is about balance. Large galaxies can hold on to what they create, allowing them to develop more complex chemistry over billions of years. Some galaxies appear red and inactive, yet they continue to grow by absorbing smaller companions. A galaxy can stop forming new stars and still increase in size and mass. In many large reddish systems, this growth happens through what astronomers call dry mergers. These are mergers that involve little or no cold gas. Instead of triggering new waves of star formation, the incoming galaxy mostly contributes its existing stars. Over time, this process builds up the outer regions, making the galaxy larger without making it brighter or bluer. Astronomers detect this kind of quiet growth by studying how galaxy sizes change across cosmic time. They also look for faint shells, streams, and gradients in starlight that hint at past mergers. This form of evolution is subtle but powerful. The central region may appear calm and unchanged, while the outskirts slowly expand. It is like a tree adding rings over time, growing outward even as its core remains stable. This process helps explain why some galaxies become enormous without ongoing star formation. Galaxy cannibalism is slow, but it can reshape a galaxy's halo dramatically. When a large galaxy captures a smaller one, the process unfolds over long periods. The smaller galaxy gradually loses energy as it orbits and is stretched by tidal forces. Stars are stripped away first from its outer regions, then from deeper within. Eventually, the smaller system dissolves into streams and arcs of stars surrounding the larger galaxy. These structures can be faint and difficult to detect, but deep imaging reveals their presence. Each stream is a record of an interaction, preserving information about the orbit and timing of the merger. Astronomers can even analyze the chemical composition of these stars to trace their origin. In this way, a galaxy's halo becomes a kind of archive. The bright central region is the main story, while the faint outskirts hold annotations from past encounters. Cannibalism is not a sudden event. It is a gradual transformation that reshapes structure over time. A galaxy's central bulge can grow as stars are scattered into random orbits. In spiral galaxies, stars usually move in orderly circular paths within the disk. However, interactions, instabilities, or minor mergers can disrupt this motion. Some stars are knocked out of their regular orbits and begin moving in many directions. This creates a thicker, more rounded central region known as the bulge. Unlike star formation, this process does not require new stars. It simply rearranges existing ones through gravitational interactions. Astronomers study bulges by measuring stellar motions and comparing them to the rest of the galaxy. Some bulges appear to have formed through violent early events. Others seem to have developed gradually through internal evolution. In either case, the bulge reflects the history of how stable or disturbed the galaxy has been. Bars in spiral galaxies can drive gas toward the center, fueling star formation. A bar is a long, bright structure of stars that extends across the galaxy's center. It is not just a visual feature. It actively influences the motion of gas. The gravitational forces within the bar can channel gas inward over time. As gas accumulates near the center, it can form dense regions where new stars ignite. This leads to increased star formation in the inner parts of the galaxy. Meanwhile, The outer regions may remain relatively quiet. Bars can evolve, becoming stronger or weaker depending on how mass is distributed. They can even disappear over time. Astronomers study bars by observing gas flows and comparing star formation patterns. A bar acts like a quiet engine of change, reshaping the galaxy from within. It shows that galaxies do not always need external collisions to evolve. Internal structures alone can guide their transformation over billions of years. Galactic rings can form after collisions, like ripples spreading through water. When a smaller galaxy passes through a larger one, it can trigger a wave that moves outward through the disk. This wave compresses gas as it travels, leading to a ring of star formation. The ring expands over time, marking the aftermath of the interaction. Astronomers can estimate the age of such rings by measuring their size and the ages of the stars within them. These rings are not permanent features. They are temporary responses to past events. They provide a clear example of cause and effect on a cosmic scale. Even after the galaxy settles, the ring remains as a visible memory of the encounter. Polar ring galaxies display stars orbiting at unusual angles, revealing complex histories. In these systems, a ring of stars and gas orbits nearly perpendicular to the main disk. This unusual structure likely forms when a galaxy captures material from another system. The captured material settles into an orbit that is tilted relative to the original plane. Because of this geometry, polar rings become sensitive probes of a galaxy's mass distribution. If the underlying gravitational field is uneven, the ring's motion will reveal it. Astronomers use these systems to study both visible and invisible matter. They provide a rare opportunity to observe two different orbital structures within a single galaxy. This makes them valuable laboratories for understanding how galaxies acquire and redistribute material. Some galaxies lack prominent spiral arms and appear smooth, dominated by older stars. Not every disk galaxy displays dramatic, well-defined spiral patterns. Some look soft and uniform, with light spread evenly across their structure. In these systems, older stars dominate, and the signs of active star formation are minimal. This absence of structure is not random. It reflects the internal conditions of the galaxy. Spiral arms depend on the presence of cold gas and organized motion within the disk. If gas is scarce, or stellar motions become more chaotic, spiral patterns can fade. Environmental effects can also play a role. A galaxy that has lost its gas through interactions or stripping may no longer sustain visible spiral structure. Astronomers study these smooth disks by analyzing their rotation and the ages of their stars. They often resemble galaxies that have entered a quieter phase of evolution. The lack of spiral arms is not emptiness. It is a clue about past events and current conditions. Irregular galaxies may appear chaotic, yet their structure reveals a detailed history. Unlike spirals or ellipticals, irregular galaxies lack symmetry and clear organization. They can look like scattered collections of stars and gas without a defined shape. However, this apparent disorder often reflects recent interactions or bursts of star formation. In smaller galaxies, even minor disturbances can produce significant changes. Their weaker gravity makes them more sensitive to external forces and internal activity. Astronomers analyze irregular galaxies by mapping where stars and gas are concentrated. They also study how different regions move relative to one another. Bright regions may appear off-center, and gas distributions can be uneven or distorted. Each of these features provides clues about past events. Irregular galaxies are especially important because they resemble systems common in the early universe. Studying them nearby offers insight into how galaxies behaved in their youth. Tidal tails are long streams of stars and gas pulled out during gravitational encounters. When galaxies pass close to one another, their outer regions can be stretched by tidal forces. This process can pull stars and gas outward into extended arcs and tails. These structures can reach far beyond the main body of the galaxy. They are not just visual features. They reveal how galaxies respond to gravitational interactions. Tidal tails can also channel gas into new regions, sometimes triggering star formation along their length. Astronomers use the shape and orientation of these tails to reconstruct past encounters. In some systems, multiple tails can form, each tracing a different aspect of the interaction. Over time, these tails may fade, disperse, or fall back into the galaxy. Even when faint, they remain evidence of dynamic evolution. They show that galaxies are not rigid structures, but flexible systems shaped by gravity. In some cases, tidal debris can form entirely new dwarf galaxies. Within tidal tails, dense clumps of gas and stars can collapse under their own gravity. These regions may become self-contained systems known as tidal dwarf galaxies. Unlike typical dwarf galaxies, they form from material that has already been processed in larger galaxies. This means they can contain relatively high levels of heavy elements despite their small size. Astronomers identify these objects by studying bright knots in tidal structures. They then measure whether these clumps are gravitationally bound. This process represents a form of cosmic recycling. A single interaction can both disrupt existing galaxies and create new ones. It highlights how destruction and creation can occur simultaneously in the universe. The Hubble Deep Field transformed our understanding by revealing countless galaxies in a tiny patch of sky. Astronomers once pointed the Hubble Space Telescope at a region that appeared nearly empty. After long exposures, the image revealed thousands of galaxies. This discovery changed our perception of the universe. It showed that even seemingly blank areas are filled with distant systems. The deep field also provided a way to study galaxy evolution across time. Nearby and distant galaxies appeared together in a single image. This allowed astronomers to compare different stages of development directly. The result was not just a collection of images, but a shift in perspective. The universe appeared more crowded, more structured, and more dynamic than previously imagined. The ultra-deep field extended this idea, revealing even fainter and earlier galaxies. By collecting light over longer periods, astronomers were able to detect extremely dim objects. These faint galaxies often correspond to very distant and early stages of the universe. The image became a deeper archive of cosmic history. It also revealed a practical truth. Many features of the universe are not hidden by complexity, but by faintness. With enough patience, more of the universe becomes visible. This deeper view allowed astronomers to study more typical galaxies from early times. Instead of focusing only on the brightest objects, they could examine a broader population. This made the picture of the early universe more realistic and detailed. The James Webb Space Telescope allows us to observe early galaxies in infrared light. It was specifically designed to detect light that has been stretched beyond the visible range. As the universe expands, ancient starlight shifts toward longer wavelengths, moving into the infrared. Webb's instruments are highly sensitive to this light, making it possible to detect galaxies that are both distant and faint. This capability opens a new window into the early universe. Galaxies that once appeared as dim or invisible objects now reveal structure and detail. Webb can also analyze the chemical composition of these galaxies through spectroscopy. This allows astronomers to study their gas, stars, and motion with unprecedented precision. As a result, early galaxies are no longer just faint points of light. They become complex systems with measurable properties. Some appear compact and intense, while others show surprising structure earlier than expected. Each observation challenges and refines our understanding of how galaxies formed. Infrared observations also help uncover galaxies hidden by dust. Dust absorbs visible light, making some galaxies difficult to detect with traditional telescopes. However, infrared light can pass through dust more easily. This allows astronomers to see regions of star formation that would otherwise remain hidden. It also helps identify galaxies that were previously overlooked in optical surveys. This is important for building an accurate picture of cosmic history. If dusty galaxies are missed, estimates of star formation across the universe can be incomplete. Infrared data also helps distinguish between different sources of energy. It can separate light from star formation and light from active galactic nuclei. This distinction is essential for understanding what powers each galaxy. In this way, infrared astronomy provides a more complete and honest view of the universe. Some early galaxies appear larger or more massive than expected, raising new questions. These observations challenge existing models of galaxy formation. Did these galaxies grow faster than predicted, or are we interpreting their light incorrectly? Lensing effects, measurement uncertainties, and assumptions about stellar populations all play a role. Astronomers carefully examine these factors to determine what is truly being observed. They compare multiple datasets and use different methods to verify results. If the findings hold, they suggest that galaxy formation may have been more efficient than previously thought. This could require adjustments to current theories. The process of questioning and verification is central to scientific progress. Each unexpected result becomes an opportunity to learn something new. Astronomers test surprising observations by refining measurements and improving models. They analyze spectra more deeply, account for gravitational lensing, and revisit calibration techniques. Small uncertainties can become significant when studying extremely distant objects. Careful cross-checking helps ensure that conclusions are reliable. This process is not about doubt, but about precision. Either the anomaly disappears under closer scrutiny, or it becomes stronger evidence for new physics. In both cases, our understanding improves. Better instruments allow astronomers to resolve faint galaxies into detailed structures. What once appeared as a single point can become a complex system when observed with higher resolution. A blurred image may reveal arcs, clumps, or multiple components when examined more closely. Spectroscopy adds further detail, showing how gas moves and how different regions behave. This transformation from dot to structure is one of the most rewarding aspects of astronomy. It shows that the universe has always been detailed. We simply needed better tools to see it. Each improvement in technology turns mystery into measurement, and measurement into new questions. Long exposure observations collect faint light gradually over time. Photons from distant galaxies arrive slowly and must be gathered patiently. By combining many exposures, astronomers can build a clearer image. This process reduces noise and enhances faint signals. The final image may appear immediate, but it represents hours or even days of observation. Deep imaging requires stability and precision. Any movement or inconsistency can blur the faint signal. The reward is access to galaxies that would otherwise remain invisible. This is why deep field observations are so valuable. They reveal what the universe looks like when we take the time to truly observe it. Space telescopes avoid atmospheric distortion, allowing sharper images of distant galaxies. Earth's atmosphere causes light to blur and shimmer. This reduces the clarity of observations, especially for faint objects. By operating in space, telescopes avoid this distortion entirely. They can produce sharper images with greater detail. This improves the ability to distinguish galaxies from stars and to measure their shapes accurately. Space telescopes can also observe wavelengths that are blocked by the atmosphere. This includes ultraviolet and parts of the infrared spectrum. By accessing these wavelengths, astronomers gain a more complete understanding of galaxies. Observing from space provides a clearer, quieter view of the universe. It allows faint signals to stand out more clearly against the background. Adaptive optics on ground-based telescopes can correct for atmospheric distortion in real time. Although Earth's atmosphere blurs incoming light, astronomers have developed techniques to counteract this effect. Adaptive optics systems measure how the atmosphere distorts light using a reference source, often an artificial laser guide star. They then adjust a flexible mirror hundreds of times per second to correct those distortions. The result is a much sharper image, sometimes approaching the clarity of space-based observations. This technique is especially effective in infrared wavelengths. For distant galaxies, adaptive optics can reveal fine details that would otherwise be hidden. It allows astronomers to resolve small structures, separate close objects, and study internal motions more precisely. This capability is crucial for understanding how galaxies evolve on smaller scales. Adaptive optics does not replace space telescopes. Instead, it complements them. Ground-based telescopes can be much larger and can host instruments that are difficult to launch into space. Together, space and ground observatories form a powerful partnership. Space provides stability and access to blocked wavelengths. The ground provides flexibility, scale, and increasingly sharp vision. Large galaxy surveys map millions of galaxies, creating a three-dimensional view of the universe. A simple image of the sky shows positions, but not depth. To build a true map, astronomers must measure distances to galaxies. They often do this using redshift, which indicates how far light has traveled. By combining position and distance, galaxies can be placed within a cosmic volume. These maps reveal structure that is invisible in flat images. Filaments, clusters, and voids emerge as part of a vast cosmic network. Different types of galaxies occupy different environments within this structure. Massive galaxies tend to cluster in dense regions, while smaller ones are more widely distributed. Each survey adds more data, refining the map and improving our understanding of large-scale structure. These maps transform the sky into something almost navigable, a three-dimensional landscape of matter. They allow astronomers to study how structure formed and evolved over time. Galaxy maps also help test how the universe expands and how dark energy behaves. Gravity pulls matter together, forming structures. cosmic expansion pushes matter apart. Dark energy appears to accelerate this expansion. The balance between these forces shapes how galaxies cluster across different eras. By measuring clustering at various distances, astronomers can test whether the universe behaves as predicted. Even small deviations can hint at new physics. These maps are compared with other observations to ensure consistency. The result is not just a catalog of galaxies. It is a measurement of how the universe itself evolves. Baryon acoustic oscillations leave a subtle imprint on the distribution of galaxies. In the early universe, matter and radiation were tightly coupled in a hot plasma. Sound waves traveled through this medium, pushing matter outward in expanding shells. When the universe cooled, these waves froze into the distribution of matter. Today, this effect appears as a slight preference for a specific spacing between galaxies. It is not visible by eye, but can be detected statistically in large surveys. This pattern acts as a cosmic ruler. Because the scale is known, astronomers can use it to measure how the universe has expanded. If the spacing appears stretched or compressed, it reveals changes in expansion over time. This method provides a powerful and independent way to study cosmology. It connects early universe physics with present-day observations. In this way, ancient sound waves still influence how we measure the cosmos today. Galaxy clustering reveals where matter has gathered, including unseen dark matter. Galaxies form in regions where matter was slightly denser in the early universe. Over time, gravity amplified these differences. This led to the formation of clusters, filaments, and large-scale structures. By measuring how galaxies cluster, astronomers can infer the distribution of all matter, not just the visible part. Different scales reveal different features. Small scales show galaxy groups and clusters. Large scales reveal the cosmic web. Clustering also varies depending on galaxy type. Some galaxies are more strongly clustered because they form in dense environments. By comparing different populations, astronomers learn how galaxies relate to dark matter halos. This makes galaxy clustering a powerful tool for understanding the hidden structure of the universe. Weak gravitational lensing gently distorts the shapes of distant galaxies, revealing hidden mass across the universe. Most lensing is not dramatic arcs or rings, but subtle stretching imprinted on galaxy shapes. This effect is caused by the cumulative gravitational influence of matter between the galaxy and the observer. Each individual galaxy shape is noisy and varied by nature. The key is to measure millions of galaxies and look for a shared pattern of distortion. That shared signal reveals how mass is distributed across large scales. Importantly, this includes dark matter, which does not emit light. Weak lensing is technically demanding because the distortions are extremely small. It requires precise imaging and careful correction for instrumental effects. When done correctly, it becomes one of the most direct ways to map mass in the universe. It does not rely on brightness or emission. It relies on gravity bending light. The resulting maps can be compared with galaxy distributions. This comparison shows how visible matter and dark matter relate to each other. It provides insight into how structure formed and evolved over time. Strong gravitational lensing can measure the mass of galaxy clusters with high precision. When alignment is favorable, lensing becomes much more dramatic. Background galaxies can appear as stretched arcs or multiple images. The exact shapes and positions of these images depend on the mass distribution of the foreground cluster. By modeling these distortions, astronomers can reconstruct the cluster's gravitational field. This includes both visible matter and dark matter. Clusters often contain far more dark matter than luminous material. Strong lensing can also reveal smaller structures within clusters. These substructures influence the lensing pattern in measurable ways. In some cases, lensing magnifies distant galaxies, making them easier to study. This provides both a measurement tool and a natural telescope. It allows astronomers to study objects that would otherwise be too faint. Some galaxies show alignment with their environment, shaped by surrounding structure. Galaxies do not always orient randomly in space. In dense regions and along cosmic filaments, their shapes and spins can show subtle alignments. These alignments reflect the tidal forces that influenced their formation. As matter flows along the cosmic web, it can impart angular momentum to forming galaxies. This can nudge them into preferred orientations. Later interactions can strengthen or disrupt these alignments. Detecting these patterns requires careful statistical analysis. They are subtle and can be easily confused with random variation. However, they provide important clues about how galaxies form within the cosmic web. They also affect weak lensing measurements, requiring careful separation of signals. In this way, galaxy alignment becomes both a subject of study and a factor to account for. Galaxies moving through clusters can lose gas due to pressure from hot surrounding plasma. Inside galaxy clusters, space is filled with hot, diffuse gas. As galaxies move through this medium, they experience a pressure similar to wind. This ram pressure can strip gas from the galaxy's disk. The outer gas is especially vulnerable. In some cases, long tails of gas can be seen trailing behind the galaxy. These features resemble streams flowing away as the galaxy moves. This process removes the fuel needed for star formation. As a result, the galaxy's ability to form new stars declines. The effect can be rapid compared to other evolutionary processes. Astronomers study these galaxies across multiple wavelengths. The stripped gas can glow differently depending on its temperature and density. This reveals how the environment actively shapes galaxy evolution. Losing gas can gradually turn a galaxy from blue to red. Blue galaxies are rich in young, hot stars. As star formation slows, these stars fade relatively quickly. Older, redder stars begin to dominate the galaxy's light. Over time, the galaxy shifts in color and appearance. In clusters, many galaxies undergo this transformation. This creates populations of older, more passive systems. The transition can occur through gradual gas depletion or sudden stripping. Stripping leaves visible signs, such as asymmetric gas distributions or trailing tails. Astronomers use these clues to reconstruct the galaxy's path through the cluster. The color change reflects an underlying physical process. It shows how environment influences galaxy evolution without requiring direct collisions. Some galaxies are surrounded by enormous glowing hydrogen clouds known as Lyman alpha blobs. These structures can extend far beyond the visible stars of a galaxy. They appear as diffuse, luminous regions of gas. The light comes from hydrogen emitting radiation after being excited by energetic processes. Because of cosmic expansion, this light is shifted into longer wavelengths. These blobs can be incredibly large, sometimes spanning regions larger than entire galaxy groups. In images, they appear as faint halos surrounding brighter cores. Astronomers study their structure to understand how gas is distributed around forming galaxies. They also provide clues about how galaxies connect to the larger cosmic web. Some are found in dense regions where many galaxies are forming. This suggests they may mark areas of intense growth and activity. These glowing clouds act like signposts, revealing otherwise invisible structures. The energy powering Lyman alpha blobs may come from several different sources. One possibility is intense star formation within the galaxy. Massive young stars emit large amounts of energetic radiation that can excite surrounding hydrogen gas. Another possibility is the presence of an active galactic nucleus. A feeding black hole can release enormous energy, illuminating the gas from within. A third explanation involves cooling radiation. Gas falling into a galaxy's gravitational field can lose energy as it cools, and some of that energy is emitted as light. In many cases, more than one of these processes may be happening at once. This makes Lyman alpha blobs complex and challenging to interpret. Astronomers analyze them using multiple wavelengths and detailed spectral measurements. They study how the light is distributed and how it moves. Each blob becomes a kind of investigation, where the cause of the glow must be carefully determined. The brightest galaxies in clusters are often located near the center of the gravitational field. In many galaxy clusters, one galaxy stands out as significantly larger and brighter than the rest. This central galaxy usually sits near the deepest point of the cluster's gravitational potential. Over time, interactions within the cluster cause massive galaxies to lose orbital energy and drift inward. As they move toward the center, they can merge with other galaxies. This leads to gradual growth, especially in the outer regions. The result is often a massive galaxy with an extended, faint envelope of stars. These central galaxies help astronomers identify the structure of clusters. Their position and properties reflect the cluster's history and mass distribution. They are the outcome of long-term gravitational processes acting over billions of years. Intracluster light is made up of stars that no longer belong to any single galaxy. Within clusters, some stars are stripped from their original galaxies during interactions. These stars drift freely, orbiting the cluster itself rather than a specific galaxy. Their combined light creates a faint glow between galaxies. This light is difficult to detect because it is spread over a large area. However, when observed, it provides valuable information. It reveals how often galaxies have interacted and how the cluster has evolved. The distribution of intracluster light can indicate whether recent mergers have occurred. Astronomers also study its color to learn about the types of stars involved. This faint glow represents a population of wandering stars, separated from their origins. It is a quiet but powerful record of past interactions. Some galaxies are extremely diffuse, appearing as faint, extended smears of light. These ultra-diffuse galaxies can be large in size, but very low in brightness. Their light is spread thinly, making them difficult to detect. They often lack a bright central core and have few distinct features. Despite their faint appearance, they can survive in dense environments like galaxy clusters. This suggests that they may contain significant amounts of dark matter. Their structure raises important questions. Why are they so spread out? Why did they form so few stars? Astronomers search for answers by studying their dynamics and environment. Some may be galaxies that failed to form many stars. Others may have been shaped by interactions that dispersed their material. Their faintness is not a lack of structure, but a clue to their unusual history. Ultra-diffuse galaxies can still be dominated by dark matter. Although they appear fragile, their internal motions often reveal strong gravitational binding. This indicates the presence of a substantial dark matter halo. Astronomers measure this by tracking the movement of stars or star clusters within the galaxy. If these objects move faster than expected based on visible mass alone, dark matter must be present. This creates an interesting contrast. The galaxy may look faint and delicate, yet be held together by a massive, unseen structure. These systems challenge assumptions about how light relates to mass. They show that brightness is not always a reliable indicator of importance. Some galaxies contain vast amounts of gas, but very few stars. In these systems, star formation has been inefficient or suppressed. The gas may be too diffuse or too stable to collapse into dense star-forming regions. Low metallicity can also reduce cooling efficiency, making star formation more difficult. Some of these galaxies are first detected through radio observations of hydrogen gas. Only later are they identified in visible light. They appear as galaxies that have the raw material for stars, but have not fully used it. This makes them valuable for understanding what triggers star formation. They show that having gas is not always enough. Conditions must also be right for stars to form. Other galaxies are rich in stars but poor in gas, showing that their fuel has been exhausted or removed. These galaxies can appear bright and stable, yet they lack the material needed to form new stars. Some have gradually used up their gas over long periods of star formation. Others have lost gas through interactions with their environment or energetic internal processes. Without fresh gas, star formation slows and eventually stops. The existing stars continue to shine, but no new ones replace them. Astronomers identify these systems by measuring weak signals from hydrogen gas and by studying their spectra. They often lack the emission lines associated with active star formation. These galaxies represent a later stage of evolution. They show that a galaxy's life is not only about growth, but also about decline. The absence of gas becomes a record of what has changed. Galaxy rotation curves revealed one of the most important clues about dark matter. Astronomers expected stars farther from a galaxy's center to move more slowly. This expectation was based on the visible distribution of mass. Instead, observations showed that stars in outer regions often move just as fast as those closer in. This result was surprising and required explanation. The visible matter alone could not account for the observed motion. There had to be additional mass extending beyond what could be seen. This unseen mass became known as dark matter. It surrounds galaxies in large halos, influencing their structure and dynamics. The discovery of flat rotation curves changed our understanding of the universe. It revealed that most of a galaxy's mass is not visible. The Tully-Fisher relation connects a spiral galaxy's rotation speed to its brightness. Faster rotating galaxies tend to be more luminous. This relationship allows astronomers to estimate distances. By measuring rotation speed, they can infer intrinsic brightness. Comparing that brightness to how bright the galaxy appears gives its distance. This method is especially useful for studying nearby galaxies. It also suggests a deeper connection between visible matter and dark matter. The rotation reflects total mass, while brightness reflects stars. The link between them hints at underlying physical relationships in galaxy formation. Elliptical galaxies behave differently, with stars supported by random motion rather than rotation. In spiral galaxies, stars move in ordered circular paths. In elliptical galaxies, motion is more chaotic. Stars move in many directions, creating a pressure-like effect that supports the system. Astronomers measure this by analyzing the spread of velocities in stellar spectra. Broader spectral lines indicate a wider range of stellar speeds. This difference in motion leads to different structures and evolutionary paths. Elliptical galaxies often appear smooth, but their internal dynamics are complex. They are systems of countless intersecting stellar orbits. The fundamental plane links an elliptical galaxy's size, brightness, and internal motion. Although ellipticals look simple, they follow a tight relationship between these properties. This relationship suggests that they are governed by common physical principles. It reflects how gravity, mass distribution, and stellar populations interact. Astronomers use this relation to study galaxy structure and evolution. When a galaxy deviates from the plane, it may indicate an unusual history. When it fits the pattern, it suggests a stable and consistent system. This hidden order reveals that even smooth galaxies follow precise rules. Globular clusters are ancient groups of stars that orbit galaxies and preserve early history. These clusters are dense and tightly bound, allowing them to survive for billions of years. Many formed during the early stages of galaxy formation. Their stars often share similar ages and compositions. By studying them, astronomers can learn about the conditions of the early universe. They act as living fossils, preserving information about past environments. Globular clusters orbit in a galaxy's halo, separate from the main disk. Their presence reveals a galaxy's deep past still in motion. The number of globular clusters around a galaxy can hint at the mass of its dark matter halo. Astronomers have found that galaxies with more globular clusters tend to reside in more massive halos. This relationship is not perfect, but it is consistent enough to be useful. The idea is that deeper gravitational wells are better at forming and retaining these dense star clusters. Globular clusters can also be detected far from a galaxy's center, making them useful tracers of outer structure. By counting and studying them, astronomers can estimate how much unseen mass surrounds a galaxy. This provides an indirect way to measure dark matter. Even small, ancient clusters can reveal the presence of a much larger invisible system. Some galaxies contain components that rotate in opposite directions, indicating a complex past. In most disk galaxies, stars and gas rotate in the same direction. However, in some systems, a portion of the material moves the opposite way. This counter-rotation usually results from external material being captured. Gas from another galaxy may settle into the disk with a different orientation. Over time, new stars form from this gas, preserving the opposite motion. Astronomers detect this by measuring Doppler shifts across the galaxy. The reversal in velocity is a clear signature of past interaction. These systems show that galaxies can be rebuilt by acquiring material from their surroundings. They preserve a record of past events within their present motion. Some galaxy centers contain dense star clusters instead of, or alongside, black holes. These nuclear star clusters are extremely compact and contain many stars in a small volume. They can form through repeated inflows of gas or the merging of smaller clusters. Over time, they grow into massive central concentrations. Their gravity influences how stars and gas move near the center. In some galaxies, both a nuclear cluster and a black hole coexist. The balance between them depends on the galaxy's history and mass. Astronomers study these clusters by observing stellar motions and light distribution. They provide an alternative view of what can exist at a galaxy's core. Not every center is dominated by a single dark object. Some are shaped by dense gatherings of stars. Many galaxies appear to grow from the inside outward. In this scenario, the central regions form first, followed by the outer disk. This leads to age gradients within galaxies. The inner regions tend to contain older, more metal-rich stars. The outer regions are often younger and more actively forming stars. Astronomers test this by studying stellar populations across a galaxy's radius. They use spectroscopy and imaging to separate different generations of stars. This pattern reflects how gas settles over time. Material with higher angular momentum tends to form structures farther from the center. As new gas arrives, it extends the galaxy outward. This process explains why many galaxies have dense cores and more diffuse outer regions. The earliest galaxies helped shape everything that followed. They did more than simply exist. They transformed their surroundings through radiation, winds, and chemical enrichment. Their stars produced energy that changed the state of intergalactic gas. Their explosions spread heavy elements into space. These elements made it easier for later galaxies to form stars and complex structures. Early galaxies also influenced the cosmic web through gravity. They helped define where matter would gather in the future. Even their black holes may have seeded later generations of active galaxies. Studying these first systems reveals how the universe set the stage for everything that came after. They are not just early chapters. They define the conditions for all later cosmic evolution. Studying distant galaxies is also a way of understanding the history of our own Milky Way. We cannot observe our galaxy from the outside, nor can we rewind its past directly. Instead, astronomers look at distant galaxies as snapshots of earlier stages. By comparing galaxies across time, they can infer how systems like the Milky Way formed and evolved. They examine how disks assemble, how bulges develop, and how star formation changes. They also observe alternative paths, galaxies that evolved differently. Some became massive ellipticals, others remained small and irregular. These comparisons help narrow down the likely history of our own galaxy. External galaxies provide a broader perspective that we cannot obtain from within. They allow astronomers to study structures like bars, rings, and interactions more clearly. Each distant galaxy becomes a natural experiment. It offers a possible version of what our galaxy once was or could have been. In this way, the study of distant galaxies is also a study of our origins. Every new survey expands our cosmic map and deepens our questions. Astronomy advances step by step. A new observation reveals more galaxies, more detail, and more complexity. A deeper view uncovers faint systems and early structures. A wider view shows how environments influence galaxy evolution. Each increase in data improves our understanding. But it also reveals new mysteries. Unexpected objects and unusual patterns challenge existing theories. Astronomers respond by refining models and gathering more evidence. The edge of knowledge becomes the most exciting place to explore. Deep surveys also become shared reference fields. Scientists return to them repeatedly, adding new wavelengths and techniques. Over time, these fields become rich archives of cosmic information. Each new layer reveals something previously unseen. The universe becomes more detailed with every observation. As we reach the end of this journey, the universe feels broader and more profound. We have traveled through distant galaxies whose light began its journey billions of years ago. We have seen how gravity shapes structure and how light carries history. We have explored clusters, streams, and hidden regions of gas and dust. We have followed patterns that stretch across the cosmic web. And throughout it all, there is a quiet sense of perspective. Each distant glow is not just a place, but a moment in time, a message that has traveled across vast distances to reach us. Some galaxies grow steadily, others are shaped by collisions and change. Some shine brightly with intense activity, others fade into a calm, older light. Together, they form a continuous story written across the sky. If you enjoyed this journey, you can support the channel with a like, a subscription, or a gentle comment. It helps more curious minds discover these quiet explorations of science, and it allows these calm, thoughtful journeys to continue. For now, there is nothing more you need to do. Let the ideas settle, like starlight fading into the horizon. Relax your body. Let your shoulders soften and your breathing slow. If you are still awake and wish to continue, another journey will be waiting for you. Otherwise, simply rest in the calm that follows. Sleep well, and good night.